Our last panelist I'm pleased to introduce is also a Clark Prize Award recipient, Dr. Perry McCarty, who is the Silas H. Palmer Professor of Civil and Environmental Engineering Emeritus, Stanford University. Dr. McCarty, as I mentioned, had received the Clark Prize in 1997, is known for his research on understanding contaminant behavior in groundwater aquifers and sediments, significantly contributed to the areas of water treatment, reclamation, groundwater recharge, and water chemistry and microbiology. Has received numerous honors, including being elected to the National Academy of Engineering and American Academy of Arts and Sciences, as well as receiving an honorary doctorate from the Colorado School of Mines. Dr. McCarty has also received the John and Alice Tyler Prize for Environmental Achievement in 1992 and the Stockholm Water Prize in 2007. Welcome, Dr. McCarty.
Thank you so much, Tom. It's good to see nice audience here. I want to talk today about producing more energy from our wastewater through anaerobic treatment. And while we're doing this, we can energy independence at treatment plants. In fact, we can be an energy producer. And well, that is not the only advantage of going this direction, because we can reduce the biosolids production by half. And as many indicate, maybe biosolids handling costs about 40% of the treatment plant operation. A lot of people indicate it's 90% of the headaches. So by this process, not only are you producing energy, but you cut your headaches in half. So let's proceed with that. Notice I have many co-authors listed from Korea. And if I can push this, what button do I push? This one? Okay. These are my colleagues in Korea. I was invited by them as a part of a program sponsored by the Korean government for senior researchers to work with some of the colleagues. The one to my right, your left, is Jae-ho Bae, a former student of mine who made this invitation, and we wrote a proposal for treatment of domestic wastewater. We're interested in seeing how low concentrations we could treat with this process. The support comes from the Korean government that I'm going to talk about. And what I want to address in here is this question of sustainability and looking at water as wastewater as a resource, not only for the water, but also for the fertilizing elements, nitrogen, phosphorus, and for energy. So these are three of the major resources we'd like to look at. Now, here, Orange County, of course, has pioneered reverse osmosis for reclaiming of water. That was the major effort there. That's certainly been spread all over the world. Singapore has at least 5 treatment plants and building more using this in water-short areas. And that's a very important process that has allowed us to expand our water resources. However, if we look at the energy requirements in doing this and compare it at the top with conventional aerobic activated sludge treatment, about 0.6 of a kilowatt hour per cubic meter is what the energy costs for doing that. If we add nitrification, we've got to put a couple tenths more onto that. There's a lot of emphasis today on aerobic membrane bioreactors. So going through membrane takes a little bit of energy, so that increases a couple tenths more, up to about 1 kilowatt hour per cubic meter. Now, if we then go to reverse osmosis, as we're doing here in Orange County, then, of course, the energy jumps up very high to 2.5. So while we're recovering water and going through more and more advanced treatment, we're putting in more and more energy into that. And what I wanted to say is, can we achieve some of this without that? The process I'd like to compare is with the aerobic membrane bioreactor of 1, going that far, and see if we can do better than 1 using an anaerobic system. So let's first look at if we just in general, if we want to look at what is the best option if we want to recover not only the water but also energy and nutrients. And one of the good examples I like to show in the Monterey Bay, where like here in Southern California, we're using groundwater, extracting groundwater, seawater intrusion. And that's what happened here. Now, this is a major agricultural area for the country, not only for the state, but for the country. And by extracting groundwater, seawater intrusion destroyed that supply for them. So they needed an alternative. They didn't have any other. They have except for the treatment plant. And so the treatment plant then took, and the interesting thing here, this is just conventional activated sludge with filtration and so forth. No nitrification, no having to remove nitrogen, because the nitrogen's a fertilizer. So they then just go through the normal 0.6 kilowatt hours per cubic meter treatment, sand filtration, multimedia filtration, and then put it onto the crops. Now, this is a major crop producing area. Something like 60% of the artichokes in the country come from this area, sprayed with this. A couple percent of the lettuce, the strawberries, the broccoli, so forth that you're eating come from this area and treated with grown with reclaimed sewage. They do not have to remove the fertilizers. The fertilizers are used here. They use it, and they grow crops 12 months out of the year. So they get that. And they also have cogeneration, digestion with cogeneration, and that produces 50% of the energy. So here they have a situation where they're recovering the water, recovering the nutrients, recovering the energy, and I think that is the way to go. Now, agriculture, using it for agriculture in this way, remember, in California, we use something like 80% of our water is used for agriculture. Agriculture is consumptive use. You can only use it once. So here, if we use it first for human use, consumptive in the cities, and then use that in agriculture, we get 2 shots at using the water. If we use it on agriculture, it's only 1. So I think doing it this way makes a lot of sense where we can do it. I know we can't do it every place, but when we think of it, I think this would be our first option, and then we have to go others depending upon where we are. Well, the question we asked is, can we treat the municipal wastewater 100% anaerobically to achieve net energy production at the same time meeting good effluent standards? So what we'd like to do is say, let's go a step further and get all the energy we can out of the wastewater. And this is just a simple picture of the anaerobic treatment, taking complex organics, goes through a lot of different organisms working together synergistically to convert the energy that's in the organics into methane gas, which we then take and use for our own uses. Now, many, many years ago, my doctoral work was on over 50 years ago on anaerobic treatment, because I thought it's such a wonderful process when we look at resource recovery. And this is indicated back then a high degree of waste stabilization, and by that I mean converting it to useful end products. Low production, and this is back then, low production of waste biological solids, which I want to really emphasize very strongly. Low nutrient requirements if you're doing industrial waste, no oxygen requirements, and of course now we're producing methane, a useful product, and a renewable fuel. So we've been working towards that for many years and trying to see how low concentration we get to, and now we're coming to doing it in sewage treatment. Now this is a diagram of a kind of a typical treatment plant. If we look down in the lower left-hand corner, we see the wastewater coming into a primary treatment tank. That's fine. We settle out the solids, set that sludge to a digester, and get the methane from that. And then it goes to an aeration tank, aerobic tank, put in air, we put a lot of energy in that, and we produce some biosludge. That goes to a digester too. That's fine. We get some energy from that. And then today, if we use a membrane reactor to clean up the solids, to get rid of the effluent suspended solids so that we can do something like using for irrigation, that's typical of what we do today. And then up there in the digester, in upper left-hand corner, we see producing methane used in cogeneration plant, where we get electricity from it, and heat. About 2/3 of the energy goes into heat, which is useful. Well, that's fine. But what we'd like to do is, because this is such a high energy user, let's get rid of that. Take it away. Let's put in there an anaerobic treatment system. So we still have the primary treatment, collecting the sludge out. Anaerobic treatment works best with soluble waste. The more biosolids we get out of there, the less trouble we have. So we use a primary treatment tank. You could do enhanced primary, that'd be fine too. But then we'll put in some kind of an anaerobic system, get more methane, still have a membrane bioreactor, and at the end there on the lower right you see a stripper, because when we do this aerobic treatment, over half of the methane stays in the water, and we got to get it out and use it. So, and we can't let it go up in the atmosphere because it's a powerful greenhouse gas. So we'll put some kind of a stripper in there and get that methane out and send it also to heat generate. So we get a lot more energy this way and a lot less biosolids. So again, the potential benefits: significantly reduce energy requirement compared to aerobic. More renewable energy is biogas. We think we can get a potential net energy producer, and greatly reduces the production of secondary sludge. So we get really reducing costs at treatment plants significantly in this manner. Well, what kind of digester should we use for this secondary treatment? And there are many out there, all using successfully. One we like for this with dilute wastewaters is the fluidized bed reactor shown in the middle there. Here's one in Taiwan. It's been treating an industrial waste for 12 years, 12-hour detention time. The wastewater has about a COD about 3,000. They've used granular activated carbon in it. The granular activated carbon, they have a recycle flow, so the granular activated carbon is fluidized. It's moving throughout the bed. Bacteria grow onto the granular activated carbon and remove this wastewater. Interesting here, this has been they filled it up, put up the activated carbon in 12 years ago. They never replaced it, never removed it. The waste goes into the bottom, comes out the top. The biosolids are so low in concentration, they have to worry about that. The treatment, it's about 3 or 4 times higher loading than an aerobic treatment system. What can be simpler than something like this? It's just a simple system sitting there. It's been operating for 12 years without any problems. So we want to use that. So this is the scheme that we started out in our laboratory studies. The one on the left side there, we decided to do this secondary treatment in 2 stages. On the left side is the first stage, is a granular activated carbon fluidized bed reactor. We have the influent going into there, treats partially, and then we have the effluent from that going into the second one. You see on the right side there. Again, it's the fluidized bed reactor with recycle water to keep it fluidized. But in this one, we put in membranes. We put in some hollow fiber membranes just to see what would happen. To our surprise, something we didn't expect, that soon as we put those in, the granular activated carbon rubbing on the surface of the membranes reduces the fouling. Now, how we do it in an aerobic system, we use a very high quantity of air, almost as much aeration as used for the treatment itself, to jiggle the fibers and to remove the biosolids so you prevent fouling. Here it's just the gentle motion of the GAC running on the surface, sort of wiping them clean, continually wiping them clean, that achieves the reduction in fouling at a very low energy cost. So this was a surprise to us, and so we've continued to study this further. Now I just want to show you something in the laboratory. When we started, we used it at a higher temperature. I don't think we should have done it. We should have started at 25. But we started at 35. But we used here was a 200 milligram per liter synthetic waste COD, 200 milligrams per liter COD, similar to sewage. In this reactor, it's 17 minutes hydraulic retention time, 17 minutes. People say it doesn't happen fast. 17 minutes, we get 90% removal. 90% removal. The loading was 17 kilograms COD per cubic meter per day, which is about 10, 15 times higher than you can do in an aerobic system. So the footprint of this is really small. And look at the production of biosolids is only 0.045 kilograms per kilogram COD, about 1/10 of biosolids production that you get in an aerobic system. So I just want to show that is our initial result. I want to show you here, if I can, I don't know if you can see the gas bubbles coming up and gas coming out of it, but you see the GAC sort of bouncing around at the top and the gas pouring out from it. This is how it's working. If we go down, we can see it's kind of a gray, but as we go down, it gets black and black, because as the biosolids build up and form that gray color, it removes to the top. It gets lighter, moves to the top, and down below it's more darker. But that's what a fluidized bed reactor looks like, operating at a 17-minute detention time. Now, what happened there? Anyway, this is fine. This is now, it goes from there to our fluidized membrane bioreactor, which is shown here. Now, on the left, we have two of them in operating. The one on the far left is the GAC is completely fluidized to cover the membranes. The one of those two on the right there, the one in the middle actually, you can see the fibers. We turned off the fluidization so the GAC would settle, so you could see the fibers. And in the far right, you can see the fibers at the top. So those are the kind of orange things are the hollow fiber membranes, and the black is the GAC in there. Now, here's a picture of it operating. You can see that little yellow little lines. You can see the GAC moving by as it's fluidized, moving along the fibers there, cleaning them out, keeping that fouling from occurring. So here we've gone through all those laboratory studies, and then we decided we wanted to go get to settled sewage, do something with real wastewater. So we've been doing this for 2 years now. This is the results, some of our results from the first year where we were operating at 25 degrees. So this is settled domestic sewage in Korea. And we have the two reactors. We see the AFBR means anaerobic fluidized bed reactor. The influence COD is 235 and BOD 105, suspended solids 93. Coming out of that reactor, now there's no membranes, we get 66, a COD coming out 30 BOD. So the first reactor does a pretty good job by itself. But then we go to the second one where we have the membrane. We see we essentially move all the suspended solids. BOD's down to 6 and the COD down to 21. So we're getting a pretty high, over 90% removal of all these at 25 degrees. Now that's the first year of operation. Then we dropped the temperature to 20, then we dropped it to 15. So the last 4 or 5 months it's been at 15 degrees, operating just about the same. And now we're just now dropping it to 10 degrees to see how low a temperature we can go with this. Now I'd like to point out the detention time in this, in the first one is only 1 hour. So that treatment efficiency with sewage, 1 hour. What comes through is primarily the suspended solids. We see a lot of suspended solids coming through. They're caught up by the membrane and held up in that second reactor, so that because the suspended solids break down slowly, but they're held up in that second reactor, so we get good transformation of that. So in that second reactor, detention time is 1.3 hours. So this is with a total detention time of 2.3 hours. And we've done that at 15 degrees at the same detention time, and now dropping to 10 with essentially the same results. So I just want to emphasize it works. Now, we've had, just to show you some other data, so this was that first year of operation at 25 degrees. The electrical energy required, this is how much electrical energy one has to put in to keep it fluidized, 0.047 kilowatt hours per cubic meter. And that's going through the membranes and everything. So that compares to, we're thinking of 1 kilowatt hour for aerobic treatment. Look at how low we get that. And we produce, just from the secondary treatment, twice as much electrical energy. Now this is how much methane we produce. If we convert it to electrical energy, we get twice as much than we need to run it. So we're an excess energy producer. And again, the biosolids production, but something surprised me, is still 0.05, about 1/10 of what you get in an aerobic treatment system. The pressure to push it through the membranes is a 0.12 of a bar, 1/10 of an atmosphere essentially, pretty low. And the flux that we're getting is 9 liters per square meter per hour for this system. Now here's, we're looking at this flux through the system. We were trying a higher one. We went up to 10. You see on the left, this is when we're doing with domestic wastewater at 25 degrees. And we see after about a month, we saw the pressure go way up. We turned off the we turned off the feed to it, and just let the GAC clean it off and work for a bit, and then it jumped up again. So we reused the 8, and that was fine. Then we tried 10 again. It fouled again quite rapidly. So we reused it to 9, and 9's what we've been using for the last year and a half, with essentially no fouling at all. So there is a level that we can use and continue to use, which we have done. I just want to show you. So now we've moved to a pilot plant. Here it is in Korea. This is 10 cubic meters per day. The upper picture tries to show the whole thing. You can see a person on the far right of that upper picture. Just want to show you a little bit the size of it. But the left, on the left there, we see at the upper picture is the first reactor, and down below on the left shows it a little bit better. So we started that one about 3 months ago. And then on the far right, we have 2 different bioreactors. And you see the lower right picture, we see a control panel. But one of the reactors, the one in the middle, has got flat sheets instead of the hollow fiber. And the one on the right has a hollow fiber. So we'll take from that first reactor, we'll be treating half of it with flat sheets and half of it with hollow fiber. Let's say it's only been operating 3 months now at the sewage treatment plant. But already we get an 85% COD removal with it. We're going to go through a cold winter in Korea, so that's going to be a real test. We hope start another one of these in Singapore. We'll start up next year. But overall, at the moment, it looks quite promising to go this. So in conclusion, I just say that wastewater reuse for agriculture and landscape irrigation, I think, is what we want to do to the extent we can, because it's going to save all resources. There's no single system that'll work every place, it'll satisfy every needs. But I think if we think of recovery of nutrients and so forth at a minimum cost, I think that's the way we should do it. Anaerobic treatment then produces energy and significantly reduces biosolids production. So we get cost savings in both ways. Now, we know we may have odors and things we have to deal with. Well, we're going to have a lot of money saved that we can help us do that, and at the same time, recovering resources. So a complete and efficient anaerobic treatment of domestic wastewater now appears possible. And the anaerobic membrane bioreactor, I think, can produce a high-quality effluent for agriculture. And I think we can even go further. If you want to put an RO system on the end of it, why not? So I think we can go there as well. So thank you, Al, very much.